Hello students and welcome back. In this video, we'll discuss the freezing point depression lab and observe how adding salt to pure water lowers its freezing point. To get started, we'll need to click on the link Freezing Point Depression. I'll cover the calculations at the end of the video, but you're asked to do some calculations while the lab is being performed. First, we'll note that there's 45.00 grams of ice in this beaker on the right. We want to record the mass of sodium chloride from the balance. If you can't see it, you can click in to view it. 3.9984 grams. Let's record that in the lab book. First, before we get started, I think we already have an image, but let's just go ahead and save another lab image. Right? And then we'll put 3.9984 grams of NaCl. Here's our new lab image. All right, so we have that. Next, we'll note that there is 100 milliliters of water in the calorimeter right here. It's not indicated in the lab, but I'm assuming that is 100.00 milliliters of water, and I'm going to put that into my lab notebook. Okay. We need to determine the mass of water from the density and then the mass of water plus ice. And again, we'll do that at the end of this lab. All right, we want to click the Save Data button, and then we want to start saving our data, but we need to wait 30 seconds for the graph to equilibrate. I think we're already equilibrated because we've been in here long enough. We see that we have 25.01 or 25.00 degrees C. Let's go ahead and click Start Saving, and we're supposed to wait 30 seconds. You can click the Accelerate button on the left over here if you want to accelerate the lab, but since we've already been in the lab for more than 30 seconds, I'm not going to do that. We're already pretty well equilibrated at 25.00 degrees C, which is room temperature. And you can see that that's also the value on the clock over here. Okay, and so we were supposed to wait 30 seconds or click accelerate, and we didn't need to do that. So I'm going to go ahead and move forward. The next step is to add the ice to the calorimeter. This coffee cup is called a coffee cup calorimeter because the coffee cup is foam and it holds the temperature. It's insulating, and it keeps the temperature pretty steady. So we're going to go ahead and put the ice into the calorimeter, and notice that our stirrer is on. We see the green button here, and if you look closely, you can observe that it's rotating. We see that the temperature begins to drop when we add the ice because the temperature of ice water is 0 degrees C. We want to wait until our temperature reaches 0. Now, we could click the accelerate button if we wanted to, but we're reaching that temperature pretty quickly, and I'm filling in the time here with talking about this process, and so I'm not going to click the accelerate button here. But the temperature the temperature of ice water in degrees C is 0. Pure water has a freezing point of 0, and when you have both phases, liquid and solid phases of water, the temperature of that ice water is 0 degrees C, and so it will equilibrate, as we expect, to 0 degrees C. And we can see that we're steadily approaching 0. We want to wait until it reaches 0 before we proceed with the next step. So I think I'll go ahead at this point and click the accelerate button until we get a good steady 0. Right, we should be accelerating a little more quickly toward 0. And I want to wait until it reaches 0, and then we will add our salt. Sodium chloride is just table salt. Now we're at 0. I'm going to turn off the accelerate button. All right, so the next step is to drag the weigh paper from the balance to the calorimeter. All right, and put it in. All right, so just drag it over until it opens and put it in. And now we'll be able to observe, we're still saving our data, a decrease in temperature. Now, what caused the decrease in temperature? We'll talk about that in just a minute. Okay, because our ice then is melting. And this is the process that causes ice cream to freeze in a traditional ice cream freezer when you add salt and ice around your ice cream. Now we're going to observe our temperature change until it stabilizes, or maybe until it begins to increase again. So we see here that we're at negative 1.61, negative 1.62. So we're still going down. We don't want to stop saving yet. I'm going to click the accelerate button, and I'm going to wait until the temperature begins to maybe increase again or stabilizes for a while. So we're still decreasing. We're still decreasing. And I'm going to wait for it to stabilize or begin to increase. I think negative 1.74 is going to be our... All right, we're going back up now. So I'm going to go ahead and click stop saving, and that's the end of our lab experiment. And next we need to do our calculations. So in order to do the calculations, we need to go to the lab book and click on our data. Okay, and we want to observe the lowest temperature. We've got time on the left and temperature on the right. We want to observe the lowest temperature. So notice the freezing point of water was at 0, and we can see that we hovered there for a while, clicking on our data. And then our lowest temperature was what? Negative 1.75. We hovered there for a while and then began to increase. So negative 1.75 was our lowest temperature, and I'm going to put that over here. Let's put that here, negative 1.75, and I'm just going to put a C since I don't have a degree symbol here. You can probably find one if you look. All right, and so that is my lowest temperature. I'm going to make a note of that in my notes over here, and then we can do the calculations. The first thing we were asked to do is to calculate the mass of water that we had in our calorimeter. So let's go ahead and do that. We had 100, and I'm going to assume 2 decimal places, 100.00 milliliters of water in the calorimeter, and we need to convert that to grams. And in order to do that, we're going to use the density. So 100.00 milliliters of water, and we're going to convert that to grams. That's 0.9997 grams of water per 1 milliliter given by the density. Okay, so 0.9997 times 100 gives us 99.97 grams of water. And we need to add that to the 45 grams of ice that we had in the beaker. So that was 45.00 grams of ice in the beaker, giving us a total of 144.97 grams of water in either ice or in either solid or liquid state. Ultimately, we'll need to use this equation. Delta T equals K sub F times the molal concentration times I, and I is the Van Hoff factor for this solid, and the Van Hoff factor for sodium chloride is 1.9, but the book tells you to use 2. So we'll use 2 for I here. So I equals 2. So next we'll need to calculate the molal concentration, and we'll talk a little bit more about the Van Hoff factor in just a minute. But in order to calculate the molal concentration, we'll need the number of moles of our solute, because molality is equal to moles of solute divided by kilograms of solvent. Okay, and we have our grams of solvent here. In order to convert that to kilograms, we need to move our decimal point 3 places to the left. And that gives us 0.1447 kilograms of water. So we have our kilograms of solvent that goes on the denominator. We need to next calculate the moles of solute. And you'll remember that we had 3.9984 grams of sodium chloride. We need to convert that to moles of sodium chloride. And in order to do that, we need to calculate the molar mass of sodium chloride from the periodic table. So the molar mass of sodium chloride is equal to 1 times the atomic mass of sodium plus 1 times the atomic mass of chlorine. So let's look at the periodic table. Sodium is 22.990. and chlorine is 35.453. So 22.990, 35.453. So we have 1 times sodium, 1 times chlorine, and that is equal to 58.443, and our units are grams per mole. Okay, so our molar mass is 58.443 grams per mole. Now we can calculate the moles of sodium chloride. So we have 3.9984 grams of sodium chloride, and that's 58.443 grams of sodium chloride per mole of sodium chloride. So 3.9984 divided by 58.443 is 0.0684 moles of NaCl. Remember, we're trying to get the delta T, the change in the freezing point, and so we need the molal concentration. We still haven't calculated that, and in order to do that, molality is equal to moles of solute, so moles of sodium chloride per kilograms of solvent, which is water. And so for our case, we have 0.06842 moles of NaCl divided by, remember our water was 0.14497 kilograms, 0.14497 kilograms of water, and that gives us a molal concentration of 0.4719 molal. So our final goal is to calculate our freezing point depression that we would theoretically have with the amount of sodium chloride that we used and compare it to the freezing point depression that we observed in our lab. So we observed a freezing point depression of negative 1.75 degrees C. So we're going to calculate the theoretical freezing point depression from this equation. Given that our I, or our Van Hoff factor, is 2, and our K sub F for sodium chloride, that's our freezing point depression constant, is 1.86 degrees C per molal. Now let's talk a little bit about why this happens before we do the calculation. And that is that if we have a network of a crystalline structure, a solid like ice, okay, it has a certain freezing point that you can look up in a book. And for our system, the freezing point of water, we have water, and its freezing point is 0 degrees C. Okay, if you disrupt that crystalline structure with a little bit of some foreign substance, then the then you lower the freezing point because you're disrupting the crystalline structure by putting in a foreign substance. And again, this has the effect of lowering the freezing point. Now, the freezing point lowering is dependent on the actual amount of species that result from the solution forming with that substance. So if you have a non-ionic solute, then you just have a 1-to-1 ratio of moles of the solute that you put in versus um, the moles of particles that you have. But if you have an ionic solute, then you'll note that the ionic solute, when it is solvated by the solvent, you get 2 moles in the case of sodium chloride, or in other words, you're going to get more moles of solute than you put in moles of the original substance. So for sodium chloride, you have approximately a 2-to-1 ratio of species for every mole that you put in of the sodium chloride. So you have a 2-to-1 ratio of ions versus moles of substance that you put in. So your Van Hoff factor is that ratio. And for our case, for sodium chloride, the Van Hoff factor for sodium chloride is 2. And that's what we have to use here. So essentially, we're doubling the effect by using an ionic substance, which is why ice is often, or salt is rather, put on roads when they freeze in order to melt the ice. Now we're ready to calculate our change in freezing point. The change in freezing point is equal to the K sub F for water, which is 1.86 degrees C per molal, times the molal concentration of our substance, times the Van Hoff factor for that substance. So the change in freezing point is equal to the K sub F for water, which is 1.86 degrees C per molal, times our molal concentration, which was 0.4719 molal, times our Van Hoff factor for sodium chloride, which we were told is equal to 2. And that gives us a theoretical change in freezing point of 1.755 degrees C, because notice that molality cancels and we're left with degrees C. So our change in freezing point will be 1.755 degrees C. Remember the freezing point of water, so our actual freezing point is going to be equal to the freezing point of water minus the change in freezing point, which would be 1.755 degrees C, which is equal to negative 1.755 degrees C. That's our theoretical freezing point for this aqueous solution. A 7 here. And we actually observed our freezing point to be negative 1.75, which is very close to the predicted negative 1.755 degrees C.